to the discussion section. So just one comment about last time. So it was pointed out to me in the lecture that I made one unnecessary assumption pointed out by Cardian. So when you solve for the zero mode in the Joachim-Rebbe soliton, right? So last time we wrote a 1D Dirac equation with a space-dependent mass term that looks like this. That's delta I dr sigma y. Okay, and this multiplied some spinner. F of r, g of r. Okay, and specifically we're looking for a zero energy solution, so we just want to solve this equals 0. This can actually be found, this zero energy solution can actually be found explicitly without assuming anything about the profile of the mass. I'll leave that as an exercise, just as a hint to the exercise, just multiply this equation by sigma y. Okay, and then you just with a scalar equation solve it, and you can show that if the profile of mu of r as we have is such that, okay, so this is mu of r, and this is r. If mu of r for r much less than capital R is say negative, and for r much bigger than capital R is positive, it doesn't matter what the profile is. You can always find a normalizable solution. So I'll leave this as an exercise. It's a very, very simple exercise. So let me just remind you where we were last time. So we were solving the PDG equation for a disk with a boundary, okay, for a T plus IP superconductor on a disk geometry. Okay, so this was our disk, radius r, and the chemical potential is bigger within the disk, bigger than 0, and then smaller than 0 outside of the disk. So this is the topologically non-trivial phase. This is the trivial phase, and we were finding the spectrum of states which are localized at this boundary. Okay, and we saw that the corresponding PDG equation has this form, so minus mu of r, and then there was this term, which was basically the pairing term delta dr plus I over r, and here it was delta minus dr plus I over r. And here there was a plus mu of r. Okay, and then we have this non-move spinner, u and v, both are functions of r. R and theta, that's equal to E times u and v. Okay, and what we found was that you could find solutions that are localized at this boundary. We wrote these solutions with a well-defined angular momentum L, okay, and the spectrum as a function of an angular momentum M. The spectrum as a function of M was delta times M plus half over R, and because of the fact that the U and V had to satisfy a periodic boundary condition as a function of theta, this M had to be a integer. Okay, so there's a linearly dispersing edge mode, which is for every energy you get minus the same energy. You get another solution with minus the same energy required by particle Hall symmetry. But these solutions sort of miss zero energy, basically because of this half. Okay, so this is basically what we showed last time. These solutions as a function of M looked like this. We got this ladder of states, but no solution actually at m equals 0 because of this extra half we got here. Okay, so to actually get a zero energy solution or a zero mode, one has to introduce a vortex. Okay, so this was the solution for the case that the order parameter of the superconductor was uniform across this disk. It turns out that to sort of correct for this factor of half, what you need to do is to twist the phase of the order parameter in a topologically non-trivial configuration, which is called a vortex. Okay, so far we've assumed that delta was independent of R. Now we're going to take a different configuration. Okay, you should really think about this delta, the order parameter, as a degree of freedom of the system. So we've found, if you like, the ground state of the system. The ground state generally will tend to have a uniform order parameter, but now we're going to look at an excitation of the system, which has some space-varying phase of the order parameter. So now we're going to take this order parameter to be a function of space. It will have some phase phi, which is going to depend on space. And what we mean by a vortex is that if we go around some point, which is called the vortex core, okay, and we look what happens to this phase, the order parameter has to be a single valued function or a continuous function, but this phase doesn't actually have to be continuous. It's continuous only mod 2 pi, okay, because it's a condensate of Cooper pairs. The wave function of the condensate has to be single valued, but the phase is only defined mod 2 pi. So in particular, we're going to consider a configuration where phi of R is just equal to theta or minus theta. Okay, so plus theta, that means that the phase phi changes by 2 pi as you go around this point. That's a vortex. Minus theta is an anti-vortex. Okay, these are two different topologically non-trivial configurations of the order parameter. And what it means for the electronic spectrum, for the BDG equation, it means that you have to give this pairing term, the pairing potential, you have to give it this extra space dependence. And the way to do it is the following. So let me write it here. Okay, so what we had before we introduced the vortex, we had a piece of our Hamiltonian, which was the pairing term, which looked like this. Sine dagger of R, we wrote everything in a continuum. Delta dx plus I dy, this was the P plus IP pairing term. Sine dagger of R. Okay, and now this delta was constant. Now I'm going to make that space dependence. There's a slight subtlety here, okay, which is that if I give this, if I make this delta space dependent, this function doesn't commute with the derivative. Where am I mean, so far I had a constant. It didn't matter where I put it, with which side of the derivative. Now it is going to matter. Okay, and in particular, this is going to be equal to e to the I phi of R now. Where am I supposed to put the e to the I phi of R? Am I supposed to put it here or there? Well, it turns out that it's not arbitrary. There is actually a correct answer. For the purpose of the BDG equation, I actually have to do it symmetrically. So what I'm going to do is I'm going to replace this by a psi dagger of R, a delta, which is a constant, okay, if you like, delta naught, times e to the I phi of 2, and then dx plus I dy, e to the I phi of 2 times sine dagger of R. Okay, so the term in the quadratic Hamiltonian is this plus remission conjugate, and that's going to be replaced for a vortex configuration by this, where this phi of R is just theta, or plus or minus theta. Okay, the reason why you need to do it like this recall that when I wrote this Hamiltonian on a lattice, I insisted that we write this delta was a matrix, Ij, right, and these signs were defined on lattice points. This looked like this, and I insisted that we use an antisymmetric form for this delta Ij. Okay, when you write the many-body Hamiltonian, this doesn't matter so much. The symmetric part cancels, but when you write the VDG equation, it actually matters. Okay, you have to use the antisymmetric form. If you write the continuum version as a matrix, you'll see that if you write it like this, you actually get an antisymmetric matrix as a function of, if you like, R and R prime. Okay, you write this in terms of a derivative of a delta function that's antisymmetric. These you need to put in both sides symmetrically. Okay, that's a technicality, but somewhat important one if you actually want to do the computation. Okay, so now I'm going to write the VDG equation with a vortex, actually an anti-vortex. For this disk, okay, but now I've located the vortex somewhere in the middle. Sorry.
Are you assuming that delta 0 goes to 0 in the core of the vortex?
Right. I actually have to assume that. Okay. If this is phi of r, right? Yeah, I've been sloppy about it. Let me clarify. This function doesn't make any sense if I approach the origin, because you see that delta cannot be continuous if delta naught is constant. Okay, because this phase is different in whatever direction you approach the origin. So this function can be okay from far away from the origin. It has to be different. So I actually have to make this delta naught somehow dependent on the radius as well. What actually has to happen is that delta naught has to go to 0 when you approach the vortex core. Okay, for this function to be continuous, it actually has to go to 0 linearly at the vortex core. This is this well-known phenomenon that if you have a superfluid, the vortex core is actually empty. Okay, there are no particles there. If you have a superconductor, it's not empty. There are particles there, but the order parameter goes to 0. It becomes like a normal metal. Okay, but what I'm doing now is I'm interested in solutions that are far away from the vortex core, solutions that are localized at this boundary. Okay, and this boundary I've assumed is at capital R, which is much bigger than delta over mu, which is psi, the correlation length. The size of the vortex core, the region where this delta, where the order parameter actually changes from its bulk value, is of the order of psi. Okay, so as long as I'm going to be interested in the solutions somewhere over here, it's not going to matter for me that this delta depends on R. Okay.
Just a curiosity, I mean, you mentioned that you have to split the phase factor to make delta Ij in the matrix antisymmetric.
Yeah.
But it seems to me that, you know, by writing it, by contracting it with the Fermion operators, you antisymmetrize it anyway.
Yeah,
so,
right.
If you left it, would you get the right answer, but you just have written it another way?
Yeah, so that's right. The subtlety is that it's the same Hamiltonian. If I look at this Hamiltonian and I write this as a general matrix, which is not antisymmetric, the symmetric part drops.
Yes.
It's just 0. It just gives me 0 to the Hamiltonian, so it's the same Hamiltonian. But when I write the VDG equation, diagonalize it, it's only the antisymmetric part that enters there. If I try to put there the symmetric part, I would get the wrong answer. Let me write the VDG equation in the presence of the vortex, where this e to the I, where phi is just minus theta. Okay, so I get an equation which is very similar to what I had before, but I just get these extra phase factors to the pairing term. So there's an e to the I theta here, delta, which is constant, okay, dr, or delta naught, let's call it delta naught, plus I over r, d theta times e to the minus I theta over 2. Okay, and then there's delta naught e to the minus I theta over 2 minus dr plus I over r times d theta e to the I theta over 2 and then the plus mu r. Okay, and as before, this acts on the spinner uv. Some energy in E times uv. Okay, and so this is a very similar problem to what we had before. You can actually make it identical to the problem that we had before by changing variables. Okay, so if you define u is equal to e to the minus I theta over 2 times some u function, u tilde, and v is equal to e to the plus I theta over 2 times v tilde. Okay, if you just substitute these new variables into this equation, you actually get that the equation looks exactly the same, but you get rid of these phase factors.
You want the same signs for the phase factors in each line, right? Because you split a phase, you want like in the top you want e to the plus I and e to the plus I, or minus and minus.
You're right. I think you're right. It's plus and plus. I think you're right. Yeah. Plus and plus. Thanks. Right. Okay. Yeah. So it's like here. I've split the same e to the I phi in both sides. Thanks. Right. So if we substitute these new functions into the equation, what we'll get is that these phase factors just cancel. Okay. And for the tildes, we just get an equation that looks exactly like the equation that we had without the vortex in. So it looks like we should just get exactly the same solutions. Okay, but notice that for these new variables u tilde and v tilde, the boundary condition as a function of theta has changed. Okay, so u and v were periodic functions of theta, but now when theta goes from 0 to 2 pi, this becomes a minus, so u tilde and v tilde have to get a minus as well to compensate for that. So that means that when we wrote the solutions in terms of angular momentum states e to the I and theta, the spectrum is actually going to look the same. It's going to be delta naught times m plus half over capital R. Okay, but the only difference is that now the allowed values of m are actually integers plus half. Okay, so the spectrum is going to look like this. This is m. Now the allowed values are actually here. This is this one is actually minus half. Okay, that's an allowed value of m. This is minus 3 halves. This is plus half, 3 halves, and so forth. Okay, so it's the same spectrum, it's the same linear spectrum as before, with a level spacing that goes like 1 over r. The only difference is that there's a shift by half a unit of m, and then there's exactly one state at 0 energy. Okay, and all the other states as before, as they have to, come in these pairs, which are symmetric around 0. Okay, so this is the advertised 0 mode. Okay, but it actually occurs on the boundary of this disk. Okay, if think about the wave function of the zero mode, it's actually, this is our disk of the P plus AP superconductor, and the wave function of the zero mode is actually localized close to this boundary, okay, somewhere here, kind of spread out. So this is one zero mode, but if you think about it, these zero modes, as we claimed last time, actually have to come in pairs. There couldn't be an isolated one. One way to see that is to go back to the lattice model. There, the whole matrix was always an even dimensional matrix, and we argued that the eigenvalues have to come in pairs of E and minus E. So if there's one a eigenvalue at 0, there has to be another one at 0. Another way to see that there actually has to be another zero energy state is to say, well, as was mentioned before, okay, so our treatment has to break down somewhere close to the origin. So let's fix that. Instead of a disk, let's think about an annulus. Okay, this is R, and there's an inner radius R prime. Okay, so now there's actually another boundary. Now I actually don't need to worry about this R dependence of delta, because R, little r, actually in the superconductor, if you like, this is a hole. My superconductor is here. In the whole delta, if you like, is 0. Okay, I don't have superconductivity there, but I have created another boundary. Okay, so I need to look for possible low energy solutions close to the inner boundary as well. And if you think about it, what I've done is perfectly valid also for the inner boundary. Okay, you can solve basically the same equations. And if you have this boundary condition that the vortex, that there's a vortex inside, so the phase of the order boundary twists by 2 pi as you go around, that's going to be true for both boundaries. So you'll actually get that there's one zero energy solution here and another one there. Okay, so indeed these solutions come in pairs, but the more general conclusion is that vortices in the P plus AP superconductor actually have zero modes in their cores. Okay, now I've kind of shown it for, strictly speaking, for a vortex that has a very large core. For a vortex that's, the core size is essentially this R prime, which is much bigger than the correlation length psi. Okay, but now I'm going to argue about continuity again. I asked, well, what happened if I took a more realistic vortex core, no hole in the superconductor, it's an actual excitation of the bulk of the superconductor. So I shrink this R prime, such that it becomes of the order of psi. Okay, so if I look at the spectrum of this hole, the spectrum of states close to this hole, there was one state at zero energy, and then pairs of states. Okay, so this is energy again, this is zero energy. There are these pairs of states, which are approximately equally spaced. Okay, so when I shrink this hole, this level spacing here, that's proportional to delta naught over capital R prime. Okay, so this becomes bigger, but there's no way I can actually get rid of this a zero mode state unless I let it hybridize somehow with a state in the outer radius, which I assume to be very far. Okay, so even if I make this vortex core very small, that state has to remain there. So this is actually a very general property of the vortex core. Okay, a vortex in P plus AP superconductor has to carry this kind of zero mode. Okay, so this zero mode is there for topological reasons. It's actually a characteristic of the phase. You can deduce it from the presence of a Chern number and the bulk and vice versa. Okay, so this zero mode cannot disappear in particular if you don't close the gap. If the gap here closes, this psi goes to infinity, and then the two boundaries can communicate, and then you can get rid of this state. Okay, so in a way, this is our first example of a defect. The vortex is a defect in the underlying phase. and it carries this topologically protected zero mode. Okay, so let me try to make a plan for the rest of this lecture. So what I was planning to talk about is basically a Majorana zero mode in 1D. Okay, somewhat briefly, I'll show that you don't actually need to start from a two-dimensional system like a P plus AP superconductor. You can get the same kind of zero mode with very similar behavior also in a one-dimensional system. I'll go through that somewhat briefly, and then I'll talk about braiding. Okay, so in particular, I'll talk about discrete braiding. How do you braid these things if they're not really mobile? Like suppose these vortices are there. Principally, you can move them around, but in 1D, these Majorana zero modes are actually not degrees of freedom of the system in the sense that the defect which the Majorana is bound to is just the edge of the one-dimensional system. What do you mean by braiding these things? These are not point objects that you're moving in a plane, but nevertheless there's a protocol that I'll call discrete braiding that can mimic braiding in the system. That's going to be useful later on. Okay, so let's see. Probably I'll go on for another until 30 past, and then we'll take a short break. Continue for another half an hour. Okay, so I'll start from this. Somewhat briefly, I assume that at least some of you have seen this in some form. Okay, to understand these zero modes in a much simpler way, it's useful to think about the one-dimensional system. Now, I'll have to be a little bit careful. I have to define what I mean by one-dimensional system. What I really mean is a wire. Okay, so there's some one-dimensional system like this, which is attached to a superconductor. The superconductor is actually not 1D. Okay, the superconductor is a bulk 3D thing. This wire by itself is not superconducting. You can't really get long-range superconducting order in a one-dimensional system. Even at zero temperature, there's going to be quantum fluctuations of the order power, which are going to destroy the long-range order. What we're doing here is not quite that. What we're doing is we have a bulk superconductor, and that's being used to induce superconductivity or pairing in our wire, in our quantum wire. Okay, so this is the so-called proximity effect. If you attach a normal metal to a superconductor, it's going to become slightly superconducting. The electrons in the metal are going to pair up as a result of pair tumbling from the superconductor. Okay, and this kind of system was first brought to our attention by Kitaev in a paper from 2003. He got the results much earlier, but I think this when the paper was published. I think some people knew about it earlier, but this is the first time it's been written explicitly, I think. Now, more recently, people have realized, I mean, it started as sort of a toy model, is a simple model that can demonstrate the principle. Later, people realized that you can actually build these things in the lab. There's some subtleties involved because, as we'll see, what you need is spinless electrons, just as in the P plus AP superconductors. Real electrons have spin. You have to get rid of that somehow. But there's a very clever way of engineering the band structure, essentially, of this wire. So what you need is basically spin orbit coupling. You also need to apply a magnetic field. and you need the induced pairing potential. Okay, so superconductivity. So if you get all these ingredients, it turns out that you can get the band structure that looks like the band structure of spinless electrons with p-wave pairing. Okay, so I'm actually not going to go into that. That's two very famous papers, one by Luchin and the other one by Berg. Okay, both from 2010. I can describe it, some of the details if anybody's interested. But the upshot for this purpose is that the simple model that I'm going to write for spinless electrons is actually really realizable in principle in the lab, and there even have been some experiments, some in Delft and some at the Weizmann Institute, that seem to see actually indications that this is actually going on. Okay, there are more platforms that are possible that may realize this physics. There's a very recent experiment at Princeton where they have magnetic atoms that are deposited on the surface of a superconductor. This is lead in the experiment. These are iron atoms. Now, this is a very clever setup. You actually control the atoms sort of one by one. You put them in some atomic locations, and you build this wire made out of these iron atoms. The iron atoms are magnetic. They're ferromagnetic. They form a ferromagnet. Okay, so this provides essentially the magnetic field. It's an exchange field. It's not an actual magnetic field, but it does the same thing. The spin-orbit coupling is there because you're sitting on the surface of a very heavy element superconductor. Okay, the spin-orbit coupling is stronger the heavier the element, so you get it from the surface actually. Okay, and this superconductivity is there because it's the surface of the superconductor, and they do STM. Okay, there's a scanning tip that's used to tunnel electrons into this thing, and they actually see something that looks very, very promising. It looks like there is the zero mode at the end of this thing. This experiment is still being interpreted, but that's the state of affairs. Okay, so this was all to say that these things may be real, actually. Okay, so let me write the model. This is often referred to as the Kitaev model. There are many things that are called the Kitaev model. Okay, so Kitaev chain model. So the model is as follows. It's a lattice model of spinless electrons in 1D, very similar to the P plus IP superconductor that we wrote for 2D. Okay, so there's a sum over J. There are electrons hopping on the lattice. Sign J dagger, sign J plus 1. Okay, this is nearest neighbor hopping. There's also a nearest neighbor pairing term. Sign J plus 1 dagger. Okay, plus emission conjugate. A minus mu sum over J is sine J dagger sine J. This is the chemical potential term. Okay, and as before, if we have a system with periodic boundary conditions, we have translation circuitry, so we can solve it by going to the Fourier space, and that's very, very easy to solve. So let me just write down the solution. Okay, EK plus or minus is equal to plus or minus square root of minus 2t cosine k minus mu squared is plus 2 delta sine k squared. Okay, so it essentially just looks like a one-dimensional cut through the dispersion that we had in 2D. Okay, and just as before, if we tune the chemical potential and we ask, is the system gapped, there's going to be a gap closing points. Okay, you can check that at k equals 0, the gap would actually close if mu is equal to plus or minus 2t. Okay, so if I plot the single particle dispersion, sort of with the delta turned off, it looks like this. And there sort of three gap ranges of the chemical potential. This is mu is less than minus 2t. This is minus 2t. It's plus 2t. okay, this is mu in the intermediate range between minus 2t and plus 2t, and this is mu above 2t. Okay, and if you try to sweep the chemical potential from one range to the other, you'll see that the gap actually closes right here. So this is a indication, it doesn't show, but this is an indication just as before, that there are actually two or more phases here. Okay, so one phase is when the chemical potential crosses the band. That's what we call before the weak pairing phase. And the other is somewhere out here, that's the strong pairing phase. And possibly there's another sort of strong pairing phase up there. Okay, and now what we'd like to understand is what happens at an interface between these two phases. Okay, or equivalently, if we're in the weak pairing phase, which turns out to be the topological phase, what happens at the boundary of that system? Okay, so we have to abandon translational invariance. We have to consider a system within an open boundary condition. So let's consider a half-infinite system. Okay, this is J, this is J equals 0, and so forth. Okay, so that's the spectrum for this system is solved in Hitai's paper, but he has a brilliant trick there. For a special point within this phase, you can really solve it in one line. Okay, many people may have seen it, but it's so simple that I'll show it briefly again. Okay, and once again, the idea is that as long as I have a gap in the bulk, and I'm looking for these protected zero modes, it's enough to find them at one point of my choice in the phase diagram. Okay, and then when I move around, as long as the bulk gap doesn't disappear, if I find one sort of isolated zero mode bound to this end, there must be another one at the other end, but as long as the correlation length is finite, as long as the bulk gap is open, these are not going to be able to disappear or move away from zero energy unless I go through a phase transition. Okay, so the trick is to look at the special point, which is mu equals 0, and t is equal to delta. Okay, so that's some point within this space. The chemical potential is right in the middle of this band. And then you can write every fermion operator psi j as a sum of two Majorana operators. Okay, this is just a change of variables. So I have two Majorana operators for every site, alpha and beta. And this is alpha plus I beta. Okay, these are Hermitian operators. They satisfy that the anti-commutator of alpha I and alpha j is equal to 2 delta ij, and alpha and beta anti-commute. Okay, so this is the, if you like, these are like the real and imaginary parts of the operator psi j. Okay, and then psi j dagger is equal just to half alpha j minus I beta j. Okay, so then you just substitute these new variables into the Hamiltonian, and you get the following form. So for this special point, okay, when t is equal to delta and mu is equal to 0, it has a particularly simple form. It looks like, let's consider a finite system with its sites. So it just looks like the sum j from 1 to n, alpha j times beta j plus 1. Okay, and that's it. So you can draw out a nice picture. Okay, so now every site contains two Majorana operators. These are my sites. There's an alpha and beta. So I essentially split every fermion operator into two halves. Okay, this is alpha 0. This is beta 0. This is alpha, sorry, I'm going to draw it opposite way, beta alpha, beta alpha 1. and 2, and so forth. Okay, and you notice that the alpha of every site is coupled to the beta of the next site, but to no other Majorana operator. Okay, so this is essentially the same construction of the AKLT Hamiltonian that we saw before for a spin 1 chain. So there you split every spin 1 to 2 spin halves. Here you split every fermion operator into 2 Majorana operators. Okay, and then this is actually very simply exactly solvable. You just, okay, sorry, there's a minus t here. Okay, t is equal to delta. Same. So the ground state is just when you satisfy that each one of these operators, alpha j times beta j plus 1, is in its ground state. They all commute with each other, so you can diagonalize all of them at once. So the ground state is just when I alpha j beta j plus 1 is equal to 1. Okay, this operator has 2 eigenvalues. You can check that it squares to 1, so it has eigenvalues plus or minus 1. You pick all the 1s here for t positive. That's the ground state. Okay, and you notice that there are 2 operators that never appear in the Hamiltonian. There's a beta naught, and there's the last alpha n. Okay, so these 2 operators actually commute with the Hamiltonian. Alpha n is equal to 0. So there are 2 zero modes. One of them localized at the left end, and the other one localized at the right end. If you solve the BDG equation, you'd get a spectrum that looks like this. Okay, 2 states exactly at 0 energy, and then sort of many states exactly at plus or minus t. Okay, and as before, I argue that if you now go away from this special point, you make t not equal to delta, or you turn on mu in some arbitrary way. Okay, since these 2 zero energy states are localized at the 2 ends of the system, they cannot hybridize as long as the correlation length remains finite, so they're stuck at 0 energy. This spectrum would widen, these states here become bands. But you must have one 0 energy solution at each end still. Okay? So it's the same Majorana 0 modes that we had before, actually. A 0 mode of the Blum-Lejeune equation actually has to be a Majorana 0 mode. It's a self-conjugate operator because you act with the particle Hall operator on it, and you get the same operator that's equivalent to complex integration. Okay, so you can achieve the same thing that we got in 2D, actually at the ends of this one-dimensional wire. Okay, and just as in the 2D case, there we argued that this 0 mode is actually a property of a topological phase in the bulk. The topological phase was characterized by a non-zero Chern number. Here there's a different topological invariant. It's not the Chern number, it's something else. It's actually a Z2 invariant. Okay, you can take 2 values, 0 and 1. I won't go into the details of that. Okay, and it's described in this paper by Type, for instance. But you can compute some invariant of the bulk, okay, without ever looking at the edges, and deduce in which of the 2 phases you are in. Okay, notice, just as an aside, that you can see already from here that there's something special in case t equals delta and mu equals 0. If you substitute that in, you get that the spectrum as a function of k is flat. Okay, which is precisely these flat bands over here. Okay, right. So now I wanna spend probably much of the rest of this lecture talking about the properties of these 0 modes, why they're non-abelian, how to break them, and what you can get out of them. Okay, but we'll probably take a short break before.
Any questions? Okay, so let us make anyway a short break, not so long.
better for the recording, so apologize if it's less pleasant. So let me try to summarize what we found. Okay, what I'll be interested in is what's the ground state manifold of the system that has n of these Majorana zero modes. Okay, and we can imagine now two different versions of such a system. Okay, the first is a P plus IP superconductor, which was actually also already kind of alluded to in Cordian's lectures. So in a slightly different context. Okay, so you have this disk of a P plus IP superconductor, and it has n vortices in it. Okay, n of these effects, so n vortices. And the other version of a setup that realizes this is an array of n over 2 wires, n over 2 of our p-wave superconducting wires. Okay, so n over 2 wires, n is even. Okay, and each one of these wires now has two n modes that are these Majorana zero modes. Okay, so microscopically these are very different systems, but in terms of the structure of the low energy subspace, or the zero energy subspace, they're very similar. Okay, and the first thing we want to know is what is the dimension of this zero energy hyperspace. Okay, so we have to do some counting. What we have to note is that every pair of these Majorana zero modes form one two-level system. Okay, in some sense the Majorana zero mode cannot be full or empty. You have to combine it with another one to form an actual two-level system. Okay, to see that, you notice that you can construct a real fermion, okay, Fj, out of two Majorana fermions in the same way that we had before. Okay, this is gamma 2j minus 1 plus I gamma 2j. You can check exactly as we noted before we didn't do it, that this F is an actual fermion. It satisfies that the anti-commutator of Fj and Fj dagger is 1. Okay, and then you can look at the occupation number of this fermion. Let's look at this thing, which is plus or minus 1, because F dagger F is 0 or 1. And that's just equal to I gamma 2j minus 1 times gamma 2j. Okay, so you can basically pick a basis of the low energy manifold where each one of these operators is in its eigenstate, which is plus or minus 1. Okay, so basically you have n over 2 bits here. So the number of ground states is actually 2 to the power n over 2. Okay, if you like, every one of these wires or every pair of these vortices forms a qubit or a two-level system. Okay, and this is what people mean when they say that the Majorana zero mode has one dimension of square root of 2. Okay, if you want to know the dimension of the ground state Hilbert space, you just take square root of 2 to the power of the number of Majorana zero modes, and that's the dimension of the Hilbert space. Okay, and very, very importantly, this ground state degeneracy, if you like, of this kind of system is topological. You can't tell in which one of these 2 to the power n over 2 states system is in by doing any form of local measurement. Okay, that's particularly intuitive in this setup, because if you think about it, what's the meaning of this number? Okay, so you have take just one of these quantum wires. That's supposed to have 2 ground states. Okay, so if you look at one of these wires, what are these 2 ground states? Well, if you think about the Hamiltonian, that didn't conserve the fermion number, but it did conserve the parity of that fermion number. Okay, so the fermion parity, which is basically minus 1 to the number of fermions in this wire, that's a good quantum number. Okay, and you can check that the meaning of these two states, okay, I haven't mentioned the gamma or the zero mode operators. Okay, so here you have gamma 1 and gamma 2. In the low energy manifold, that's just equal to I gamma 1, gamma 2. To check this. Okay, and this is a good quantum number. Every state can be labeled by this, by its fermion parity. And the claim is that if you're in the topological phase, these two states are actually degenerate. Okay, they actually have the same energy up to an exponentially small correction in the system size. Okay, and this parity of the fermion number is a very non-local property. If you take if you measure anything local, okay, you measure the local density here or the local spin here or any quantity that you like, that's never going to tell you what's the total parity. The only way to really tell that, if you like, is just to take a snapshot of the whole system at once and just count how many fermions are in there, in the ground state wave function. Okay, that's a very non-local operation. That's why this information is very hidden. Okay, for instance, one way you can imagine measuring that is to bring these two things actually close together. I mean, suppose you had some knob that sort of shrinks this wire. For instance, you could control the chemical potential locally. We saw that a topological phase is achieved in a certain range of chemical potential. So suppose you have a gate voltage that you can tune, such that this becomes very small. If this is small enough, of the order of the correlation length, the wave functions of these two Majorana zero modes are going to overlap. They're going to split out from zero energy. Okay, so these two states are not topological anymore. And then you just, if you like, measure the energy of the system, and that tells you in which of the two states you're in. Okay, and as how do you measure energy? Well, it turns out that when this happens, when these two overlap, also the local charge is going to be different for the two states, and local spin is going to be different for the two states, and so forth. That's going to be reflected in some local observable. Okay, so this is why people are so excited about this phase, this non-locality, the fact that the information that's encoded in this qubit is very well hidden. Okay, it's hidden for us, it's also hidden from the environment. If you created the system in some superposition of these states, it's going to be very hard to decohere the phase information within that state, because to decohere you have to dephase, you have to couple differently to different components of the wave function, and the environment couples the same to all of them. Okay? Usually, generally speaking. Okay, and then the natural question is, well, if this information is so well hidden, how are we going to manipulate this system? Okay, and for that we need some topological manipulations. And for the case of the vortices, we already know that these act as anyons. You can exchange them, and you get some non-trivial gate or unitary operation that's acting on this ground state manifold. Okay, so we're going to talk about grading. Okay, so now I'm going to start from the case of the superconductor, which is kind of conceptually somewhat easier. So here are here's my 2D P plus AP superconductor, and I have two of these vortices, gamma 1 and gamma 2. And suppose that using some scanning tip, I can actually move these things around, and I can exchange them. So in particular, I move them very slowly, okay, slowly on the scale of the gap. That means adiabatically. And at the end, the vortex that used to be here is actually there, and vice versa. The Hamiltonian of the system is the same as it was, but there's no guarantee that within this 2 to the n over 2 fold ground state manifold, the state is the same as it was. Okay, and I want to know, if I started from a given state, which state I ended in. Okay, and there are various ways to derive the answer. One, which was mentioned by Carl Jan, is to look at the many-body wave function of this superfin actor. You can read off the answer from there. I'm going to take a different approach. Okay, so I'm actually going to drive it in a couple of ways. One particular simple way is the following. Well, I have some unitary U12. Okay, and under this exchange, this unitary represents this exchange in the ground state manifold. Under this exchange, if I started from some wave function, psi final is just a U12 times psi initial. Okay, and this U12 is nothing but the evolution operator, the adiabatic evolution operator that I get for this time-dependent Hamiltonian that represents this operation. Okay, so I want to find this matrix U12. Okay, and first, instead of finding the matrix, I'm going to ask what happens to the operators gamma 1 and gamma 2, the zero mode operators, when they're conjugated by this matrix. Okay, so gamma 1 goes to some new operator, gamma 1 prime, which is equal to U12 dagger times gamma 1 times gamma 2, and gamma 2 in the same way goes to gamma 2 prime. U12 dagger gamma 2 U12. Okay, so I want to know what happens, how do these operators transform under this unitary? Okay, so one thing I know on physical grounds is that if I start from the operator gamma 1, this vortex, it's bound to the core of this vortex. Okay, its wave function, if you like, is localized at this vortex. This vortex just is transported here. So at the end of the day, it's going to be proportional to gamma 2. Okay, so gamma 1 prime is going to be proportional to gamma 2. And in the same way, gamma 2 prime is going to be proportional to gamma 1. And the only thing that remains for me to do is to determine the amplitude in front of these operators. Okay, so it turns out that I can't quite determine them uniquely, but I can tell what they are up to a minus sign. Okay, so the first thing to note is that these are Majorana operators. They satisfy also algebraic rules. In particular, their square is 1. That's not going to be changed by this unitary. Okay, so at every intermediate step, I'm going to get a zero mode operator which squares to 1. So that means in particular that the proportionality constant here is constrained to the either plus or minus 1. It can be nothing else. Okay, and the same thing here. So the only thing which is left for me to do is to determine the space, which is plus or minus 1. Let me assume that gamma 1 prime is just equal to gamma 2. Okay, and then I notice that I can ask, well, what is I gamma 1 prime, gamma 2 prime? That, if you like, is the fermion parity of the system in the low energy sector. Okay? If I had only these two vortices and nothing else, everything else was very far away, there are two ground states which are characterized by a different fermion parity, and the fermion parity operator that represents that is precisely this, I gamma 1 prime, gamma 2 prime. Now, this fermion parity operator is going to have to be preserved by this unitary, because this unitary never adds fermion to the system. Okay, so this has to be equal to I gamma 1 gamma 2, and since I argued that gamma 1 prime is proportional to gamma 2, and gamma 2 prime is proportional to gamma 1, you see that I can substitute that in here, they interchange. I get a minus sign when I try to interchange them back, and the only way to correct for that minus sign is if gamma 2 prime is equal to minus gamma 1. Okay, so this is actually what happens to these operators under Berg. And from that, you can sort of guess the form of the actual operator U12. That operator has to be a function of basically of gamma 1, gamma 2. That's the fermion parity operator, because it has to commute with that. In some sense, that's the only operator in this twofold Hilbert space that it can depend on. So it has to be some function of this, and it turns out that the function that does the trick is just some phase, we'll talk about in a moment, times the operator pi over 4, gamma 1, gamma 2. Okay, and you can check explicitly just by substituting this in here and there that these relations hold. Okay, this exponential of this 2 by 2 matrix is very simple because this is just plus or minus I. Okay, the eigenvalues of this are just plus or minus I, so you can write it explicitly as e to the I phi 1 over root 2 times 1 plus gamma 1 gamma 2. And then you just use the rules of Majorana fermions and you get exactly that. Okay, now this phase is an overall phase of the unitary. That's something that I actually can't determine this way. And I'll talk a little bit about that phase later on. Let me just mention that this phase, one of the reasons why this phase is kind of hard to define, the way I think about the grading process this way, is the following. So if you really think about this as an evolution operator, okay, so there's some time-dependent Hamiltonian. In principle, there's no guarantee that the ground state energy of this time-dependent Hamiltonian, for instance, that I follow, and I do it adiabatically, I follow the ground state, that a ground state energy can change as a function of time, for instance. There's some dynamical phase that I accumulate. Okay, if you think about the adiabatic theorem, the phase that you get is a Berg phase plus a dynamical phase. This phase over here actually knows about that dynamical phase in a way. Okay, so without specifying what exactly the path is here, which I haven't, I actually can't tell you what this phase is. Okay, and you can ask, well, what about the Berg phase? You can separate the phase into a geometric part and a dynamical part. Can you at least define the Berg space part of this operator? Okay, so the answer is that it depends. Okay, it actually depends on the system. In the particular example that I'm showing you here, that's kind of hard. I mean, these are vortices. They have long-range interactions. They actually are not point-like particles. In a superfluid, at least the vortices have an interaction between them that falls off only as a log. Okay, so this phase really depends on how I do the path, and it can depend on the path even if these vortices are very far away. They feel each other. Okay, what's protected is only the relative phase between the two states. Okay, I have the two states 0 and 1. One of them under this exchange gets a phase of e to the I phi plus pi over 4. The other one gets e to the I phi minus pi over 4. That part is protected. Okay, that part doesn't depend on all sorts of details, but the overall phase would, even if they're very far apart. Okay, if I had a system where these are really point-like excitations, that would have to be, if you like, a charged superconductor, where the interaction between vortices is actually short range, or if these are quasi-particles and n equals 5 halves quantum Hall state, then these are point particles. Then there's yet another subtlety. Okay, you get within this phase here, you also get the Berg phase that's coming from the Bohm effect. But you can subtract that also, and there is actually a phase which is universal. Okay, you can define it as a universal phase. You can actually read it off from the operator product expansion of these two quasi-particles, as Karian explained. And this phase over here of basically pi over 2 is the difference between the two phases that you get in the two fusion channels of these two quasi-particles, basically plus or minus 1. Okay, so that is a long story, but just to get to the bottom line, for many purposes, it actually won't really matter what this phase is. It's just a global phase, if you like. Okay, a global phase of the wave function in quantum mechanics generally is not observable on its own. The relative phase here is going to be the important part. That's the part that actually gives a different phase to the two states, and that's always going to be protected. That's going to be topological. Okay, but for some reason it is, for some purposes it is important. If you do some interference, you might observe that phase as well. Okay, but for now I won't discuss it. I would sort of focus on this part alone. So I'm really asking, what is this unitary operator U12 up to a phase? Okay, let me mention that there's a very nice argument, physical argument, to understand this result that was invented by Ivanov. This is 2001. Okay, you simply recall that if you have a vortex in a superconductor and you take a fermion around it, okay, so the fermion is like half the Cooper pair. The Cooper pair requires a phase of 2 pi. When you do that, the fermion requires a phase of pi. So you can think about the vortex as carrying the branch cut, where the phase of the vortices jump by pi each time you cross this branch cut. Okay, and then if you think about this process where you exchange two of these vortices, okay, each one of them has its own branch cut, and you take this one to here and that one to there. Each one of them carries a fermionic zero mode, gamma 1 and gamma 2, and this zero mode is made out of some fermions, and their phase is not single valued, it jumps by pi. In a certain gate choice, each time they cross this branch cut, and if you sort of follow through what happens during this process, you'll find that the gamma 1 has to cross the branch cut of gamma 2, but not the other way. Okay, so this would tell you that gamma 1 goes to minus gamma 2, and gamma 2 goes to gamma 1. Okay, that's opposite in sign from what I had there, and it would be the same sign if I did the gradient the other way. Right, so, okay, so what I want to discuss next, and I'll just set it up and maybe continue later. I'm going to formulate this grading in a different way that's going to be easier to generalize to other types of anionic defects that are not Majorana. Okay, and to set that up, let me ask, this was shortly after people thought about Majoranas and wires. You can ask, well, what about the zero modes at the ends of wires? So, unlike the vortices, they really cannot be thought of as point-like objects in a two-dimensional plane. They're really externally imposed. Okay, so we have these n wires. We have the topological degeneracy in the system, but do we have some sense of braiding? Okay, so how do I exchange these two zero modes, or even more than that, you can say, well, I just rotate the wire. But what about these two zero modes? So can I actually exchange them? Okay, so it turns out that you can, and that actually also gives you a very explicit way to compute what this braiding is. And the setup to consider to do that is the following. So what I want to do is to describe this grading process not as a process in real space, but as a process in some Hamiltonian space. Okay, I just want to look at some time-dependent Hamiltonian and find the evolution operator of some adiabatic path. Okay, now if I only have two of these Majoranas, that's going to be hard. Because one thing I'm going to insist on is that if I exchange gamma 1 and gamma 2, at every intermediate step, they're going to remain as zero modes. They're going to remain stuck to zero energy. Okay, because if they don't, I'm going to acquire some phase difference between the two states that is not universal, is not topological. Okay? It's going to depend on my path. So what I'm going to do to exchange 1 and 2 is the following. Okay, here I'm going to gamma 1 and gamma 2. What I'm going to do is actually introduce two auxiliary Majoranas. Suppose I have another wire. Okay, so I have also gamma 3 and gamma 4. Okay, and these are going to help me exchange gamma 1 and gamma 2. And the way I'm going to do that is I'm going to imagine that I can control, if you like, the length of each one of these segments. So the segment 3, 4, the segment 1, 3, and the segment 3, 2. And if I make the corresponding segment short enough, the two Majoranas at the ends are going to start coupling to each other. Okay, there's a wave function here, there's a wave function there. These wave functions decay as e to the minus x over xi. Psi is some correlation length, x is the distance from the end. If the length of the wire is shorter than psi, the corresponding Majoranas are going to split. Okay, and what I'm going to do is control all of these lengths, or equivalently, I'm going to have an effective Hamiltonian. Okay, this is a Hamiltonian that acts on the low energy subspace. Okay, I'm going to basically project my many-body Hamiltonian onto the low energy subspace of these four Majoranas. So it's a finite matrix. Okay, and I write that as sum over I and j, go just from 1 to 4. I, some coupling constant j I j, this is a function of time, times gamma I gamma j. Okay, and what I'm going to do is that I'm going to consider some path, some closed path in this Hamiltonian space that's going to implement the braiding for me. So it's like a protocol that implements braiding. Okay, this was introduced, I think, by Andrea. This is probably 2011. Okay, so I'm going to talk about non-contractible paths, not in real space, but in this Hamiltonian space. And if I find a path that cannot be contracted adiabatically to 0, that's actually important. Okay, because if it can, then it's trivial, then it shouldn't do anything. On the low energy subspace, if I find such a path, there's a chance that the corresponding unitary evolution operator would be non-trivial. And it would also be important that the result of this evolution, okay, this is some abstract J space, these are the different J's. I'll have some path in this parameter space, and there's some obstruction to actually shrink this path to 0. And moreover, it would turn out that if I deform this path, just as was argued for the braiding in real space, if I deform this path around some given path, as long as it encloses the same obstruction, the resulting unitary matrix that I get at the end, U12, doesn't depend on the precise shape of the path. Okay, so let me just set it up a little bit more and then I'll break. Right, so my obstruction is basically going to come from the fact that I insist that at every intermediate step of this process, the ground state degeneracy that I started from is going to remain fixed. Okay, so I've introduced my two auxiliary Majoranas that are 3 and 4. So I don't want to get any extra degeneracy either. So if my first step, or if you like my initial and also final Hamiltonian, is going to be such that 3 is coupled to 4. Okay, so there's a J34, which is non-zero. So my H initial, H of time equals 0, is just a Ij34, say positive, it doesn't really matter, gamma 3, gamma 4. Okay, so I have a finite Hilbert space here. I have 4 Majorana zero modes. So I start, before turning on this J34, I start from a Hilbert space which is actually 4-dimensional. Okay, it's 2 to the power n over 2. And out of these 4 states, I actually split the ground state degeneracy partially into 2 and 2. Okay, there are 2 ground states and 2 excited states, but as long as I don't couple 1 and 2 to anything, these two-fold ground states are going to remain degenerate. Okay, and now I want to start changing the Hamiltonian, but I'm going to change it in a way that the ground state degeneracy is going to stay the same. Okay, and it turns out that there's a very general way to determine what is sufficient to lift the ground state degeneracy and what isn't. Okay, so what I'll start to do, for instance, is I'm going to start turning on the gamma 1, gamma 4, the J11, sorry, gamma 1, gamma 3, the J13 term. Okay, adiabatically. And it turns out, for instance, that as I do that, I actually don't lift the two-fold ground state degeneracy. I change the wave functions of the zero modes, or I change the wave functions of the ground states, but I don't change the fact that there are 2 states that are exactly degenerate. And the condition for that is actually very simple. As long as gamma 2 remains decoupled throughout this process, okay, from either 1, 3, or 4, then I'm actually guaranteed that the ground state degeneracy is the same. So for any value of J13, and even if I turn on the J14, for any arbitrary value of these 3 parameters, the ground state degeneracy is actually at least twofold. Okay, so that allows me, for instance, to turn this J13 on in some way and turn a J34 off. As long as they're not both 0 at the same time, the ground state degeneracy remains the same. So at the end of step number 1, what I'm going to do is I'm going to end up in this configuration. So this is 1, 3, 2, 4. Okay, so now 1 and 3 are coupled. They're split off from 0 energy, but 2 and 4 are actually decoupled. Okay, and so on. So I'm gonna let me just draw the whole process and then discuss it next time. So this is actually the first step. There are 3 steps. Step number 2. That's going to be the step where I start turning 3 to 4 on. Okay, so I go from 1 to 3 and to 2 to 3. So this is 1, 2, 3, 4. I start turning on 3 to 2, and at the end of this step, I have 3 coupled to 2 and nothing else. Okay, 1, 2, 3, 4. And then in the last step, step number 3, I'm gonna start turning on 3 to 4 back. Okay, so I turn on 3 to 4 gradually. 4. And by the end of this third step, I actually go back to the same Hamiltonian that I started from, such that 3 to 4 is turned on. Okay, so it's a closed path in Hamiltonian space of these Jij's, but the wave function doesn't actually return to itself. Okay, so it turns out that the wave function gets this unitary, which is precisely the unitary of Berg. Okay, and we'll discuss that in this afternoon. All right, any questions?
So the parameter space is effectively three-dimensional. Do I see that right?
Yes.
Okay.
Right. In this example, the parameter space. Well, okay, with a caveat. So in the path that I've described here, the parameter space is three-dimensional because there are three couplings that are turned on and off, and there's a nice three-dimensional picture that I'll draw, which will show what the path is. But it's a little bit of a cheat, because if you think about it, the way I want to think about controlling these different JIJs is by shrinking, as I said, sort of these wires. Okay, that's also the way it was proposed in this paper. Okay, but you see that, for instance, in step number 1, there's some intermediate step where 1 is coupled to 3 and 3 is coupled to 4 at the same time. Okay, so that means that you're physically close. Okay, you can easily imagine that 2 is decoupled throughout this process because you just make it far away. Okay, but there's no reason that 1 won't be coupled to 4 at the same time. Okay, that's an extra parameter. So to really show that this acts like braiding, what we'll have to do is to, this is one explicit path that I can compute, but what I need to argue is that the result of this path is independent on whether in this intermediate step I also turn on some 1 to 4. The parameter space is actually bigger, okay, bigger than 3. Okay, but that turns out to be true. If you deform the path in an arbitrary way in the JIJ space, as long as 2 is decoupled, that's the important part, then you get the same result. You get the same U1, 2.
Observations?